This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is center tapped and distribution transformers. Our objective is to take a closer look at center tapped transformers and discuss the role of distribution transformers in split phase or single phase three-wire systems. Recall in the transformer connection diagrams lecture, available at the Big Bad Tech channel, we introduced phase dot notation, where the terminals identified with the phase dots simultaneously achieve the same polarity. For example, consider a 1-to-1 isolation transformer with a 240 volt, 200 amp rated primary and secondary windings. This transformer will be capable of transferring 240 times 200 or 48 kilovolt amperes of power without physical or electrical contact. Isolation between the primary and secondary windings allow a degree of flexibility in the system, and that the primary side could be grounded and the secondary side could be ungrounded or floating, or vice versa. For now, let's assume both sides are floating without reference to ground. If terminals H1 and L1 are identified with a phase dot, this means when H1 peaks positively, so does L1. Similarly, when H1 valleys negatively, so does L1. Long story short, H1 to H2 is perfectly in phase with L1 to L2. Given a 1-to-1 turns ratio, secondary winding L1 experiences 240 volts RMS. Any load between terminals L1 and L2 would experience 240 volts. If we were to add a tap on the secondary winding called N exactly in the center, such that an equal number of turns appear between both halves of the secondary, we could think of this as two secondary windings with a phase dot at L1 and at N. Keep in mind this system is presently floating with no reference to ground. When H1 to H2 peaks positively, a voltmeter placed positive to negative L1 to N would also peak positively, as would a voltmeter placed positive to negative N to L2. Similarly, when H1 to H2 valleys negatively, a voltmeter placed positive to negative L1 to N would valley negatively, as would a voltmeter placed positive to negative N to L2. Again, given this system is presently floating with no reference to ground, this would result in three possible outputs: L1 to L2 with 240 volt differential, L1 to N at 120 volts, and N to L2 at 120 volts, all in phase with one another. This should be a review of the contents we previously discussed in the transformer connection diagrams lecture. Let us now consider these two subtle modifications to this system. 1. Central tap N, henceforth called neutral, is ground referenced. 2. Both voltmeters use the neutral connection as the reference. Voltmeter 1 measures L1 to neutral, positive to negative. Voltmeter 2 measures L2 to neutral, positive to negative. Importantly, ground referencing the center tap does not change the location of the phase dots. When H1 is higher or more positive than H2, L1 is higher or more positive than N, and N is higher or more positive than L2. This also means L2 is lower or more negative than N. I say again, when N is higher or more positive than L2, this simultaneously implies L2 is lower or more negative than N. When N is ground referenced and voltmeter 2 uses the neutral connection as the reference, it can be said when H1 to H2 and L1 to L2 peak positively, L1 also peaks positively and L2 valleys negatively. With ground as the established reference, L1 and L2 are equal in magnitude yet perfectly out of phase with one another. I say again, with ground as the established reference, L1 to neutral and L2 to neutral are equal in magnitude yet perfectly out of phase with one another. If we were to express these voltages as phasor equivalents, H1 to H2 would be 240 volts at an angle of 0 degrees, L1 to neutral would be 120 volts at an angle of 0 degrees, and L2 to neutral would be 120 volts at either positive or negative 180 degrees. L1 to L2 would be 120 at an angle of 0 degrees minus 120 at an angle of 180 degrees, or 240 volts at an angle of 0 degrees. This is what is known as a split phase or single phase three-wire system, where the three wires in question are L1, L2, and neutral. This is a common type of residential power distribution system in the United States. 240 volts comes into a distribution transformer and it's split into two 120 volt phases, L1 to neutral and L2 to neutral, equal in magnitude yet perfectly out of phase with one another. This type of system additionally allows 240 volts between L1 and L2 for larger electrical loads like water heaters, ovens, dryers, car chargers, and outlets for equipment like welders. Let's explore the operation of a split-phase system by way of an illustrated example. You note I've included a mechanically interlocked 200 amp circuit breaker on both L1 and L2. You can think of this as a master switch that selectively enables or disables all loads. Anytime current is in excess of 200 amperes, the circuit breaker opens up and disables the complete system. Customarily, an attempt is made at balancing loads in a split-phase system such that L1 and L2 experience the same amount of power, or nearly so. Consider the lighting in one section of a house modeled as a purely resistive 40 ohm load on L1, and lighting in another section of the same house also modeled as a purely resistive 40 ohm load on L2. Both these loads are serviced by 10 amp circuit breakers on the hot or high side of the given phase. An application of Ohm's law solving for current demonstrates the first lighting load draws 3 amps at an angle of 0 degrees. A subsequent application of the AC power formula demonstrates the first lighting load consumes 360 volt amperes of apparent power, of which 360 watts is directed towards real power and 0 VARs is directed towards a reactive interchange. Similarly, an application of Ohm's law demonstrates the second lighting load draws 3 amps at an angle of 180 degrees, equal in magnitude, yet perfectly out of phase with the lighting load on L1. A subsequent application of the AC power formula demonstrates the second lighting load also consumes 360 volt amperes of apparent power, of which 360 watts is directed towards real power and 0 VARs is directed towards a reactive interchange. In totality, this system is supplying 360 plus 360, or 720 volt amperes. If we were to assume this transformer is 100% efficient, we can say that the primary must also provide 720 volt amperes of apparent power, all of which is directed towards real power. An algebraic manipulation of the AC power formula, solving for current, demonstrates the 240 volt primary draws 3 amps at an angle of 0 degrees. With the system in the presently balanced condition, you will note that the current drawn by each load is equal in magnitude, yet perfectly out of phase with one another. It's helpful to remind ourselves that phasors are merely shorthand representations of sinusoidally oscillating conditions. At a given moment when 3 amps of current enters lighting load 1, 3 amps of current happens to be leaving lighting load 2. The return path afforded by the neutral line is the current in lighting 1 plus the current in lighting 2. Given current in the lighting loads are equal in magnitude and out of phase with one another, current in the neutral line, while in the balanced condition, is 0 amps. This is true only in the balanced condition. Let's say a heater modeled as a 30 ohm purely resistive load and protected by a 20 amp circuit breaker on L1 turns on. The presence of the heater in no way, shape, or form affects the two lighting loads. They continue to draw 3 amps of current out of phase with one another, and each consumes 360 watts of power. An application of Ohm's law demonstrates the heater draws 4 amps at an angle of 0 degrees from L1. An application of the AC power formula demonstrates the heater consumes 480 volt amperes of apparent power, of which 480 watts is directed towards real power and 0 VARs is directed towards a reactive interchange. In totality, this system is now supplying 360 plus 480, or 1,200 volt amperes. If we were to assume this transformer is 100% efficient, we can say the primary must also supply 1.2 kilovolt amperes of apparent power, all of which is directed towards real power. An algebraic manipulation of the AC power formula, solving for current, demonstrates the 240 volt primary draws 5 amps at an angle of 0 degrees. With the system in the presently unbalanced condition, you will note that current drawn from L1 and L2 are no longer equal in magnitude with one another. L1 provides 3 amps at an angle of 0 degrees to lighting load 1, plus 4 amps at an angle of 0 degrees to the heater, or a total of 7 amps at an angle of 0 degrees. Whereas L2 provides only 3 amps at an angle of 180 degrees to lighting load 2. The return path afforded by the neutral line carries current to the first lighting load, plus current to the heater, plus current to the second lighting load. Substituting in our given values demonstrates current in the neutral line is 4 amps at an angle of 0 degrees, i.e. the degree of imbalance between that drawn from phases L1 and L2. Note the state of balance of a distribution transformer is also affected by the inductive or capacitive nature of loads on given phases. Let's say a motor modeled as a 30 ohm at an angle of 30 degrees complex impedance and protected by a 20 amp circuit breaker on L2 turns on. As previously, the presence of the motor in no way, shape, or form affects the two lighting loads nor the heater. The lights continue to draw 3 amps of current out of phase with one another and each consume 360 watts of power. The heater continues to draw 4 amps of current, continues to consume 480 watts of power. An application of Ohm's law solving for current demonstrates the motor draws 4 amps at an angle of 180 degrees minus 30 or 150 degrees. An application of the AC power formula demonstrates the motor consumes 480 volt amperes of apparent power, of which 415.7 watts is directed towards real power and 240 VARs is directed towards a reactive interchange. In totality, the system is supplying 360 plus 360 plus 480 plus 415.7 watts, or 1,615.7 watts of real power and 240 VARs of reactive power, or a total of 1,633 volt amperes of apparent power. We could say the primary must also provide roughly 1.6 kilovolt amperes of apparent power. An algebraic manipulation of the AC power formula solving for current demonstrates the 240 volt primary draws 6.8 amps at an angle of negative 8.4 degrees. With the system in the presently unbalanced condition, you will again note that current drawn from L1 and L2 are no longer equal in magnitude nor perfectly out of phase with one another. L1 provides 3 amps at an angle of 0 degrees to lighting load 1, plus 4 amps at an angle of 0 degrees to the heater for a total of 7 amps at an angle of 0 degrees. Whereas L2 provides 3 amps at an angle of 180 degrees to lighting load 2, plus 4 amps at an angle of 150 degrees, or a total of 6.8 amps at an angle of 162.8 degrees. The return path afforded by the neutral line is current through the lighting load 1, plus current through the heater, plus current through the second lighting load, plus current through the motor. Substituting our given values demonstrates current in the neutral line is 2.1 amps at an angle of 75 degrees, i.e. the degree of imbalance between that drawn from phase L1 and from phase L2. Split-phase systems still offer 240 volts for larger loads. Consider a clothes dryer, modeled as a 20 ohm at an angle of 10 degree complex impedance protected by a mechanically interlocked 40 amp circuit breaker between L1 and L2. As previously, the presence of the dryer in no way, shape, or form affects the two lighting loads, nor the heater or the motor. The lights continue to draw 3 amps of current out of phase with one another, and each continue to consume 360 watts of power. The heater continues to draw 4 amps of current and continues to consume 480 watts of power. The motor continues to draw 4 amps at an angle of 150 degrees and continues to consume 415.7 watts of real power and 240 VARs of reactive power. The dryer experiences the full differential of 240 volts at an angle of 0 degrees between L1 and L2. An application of Ohm's law solving for current demonstrates the clothes dryer draws 12 amps at an angle of negative 10 degrees from the 240 volt secondary winding. An application of the AC power formula demonstrates the clothes dryer consumes 2,880 volt amperes, or roughly 2.9 kilovolt amperes of apparent power, of which 2,836.2 watts, or roughly 2.8 kilowatts, is directed towards real power, and 500.1 VARs is directed towards a reactive interchange. In totality, the system is now supplying 360 plus 360 plus 480 plus 415.7 plus 2.8 kilowatts, or roughly 4.5 kilowatts of total real power, and 240 plus 500.1 VARs, or 740.1 VARs of total reactive power, for a total of roughly 4.5 kilovolt amperes of apparent power. If we were to assume this transformer is 100% efficient, we could say the primary must also provide 4.5 kilovolt amperes of apparent power. An algebraic manipulation of the AC power formula solving for current demonstrates the 240 volt primary draws 18.8 amps at an angle of negative 9.4 degrees. Given the clothes dryer does not necessitate the neutral line, current in the neutral line remains 2.1 amps at an angle of 75 degrees, i.e. the degree of imbalance between that drawn from phase L1 and phase L2. You note the single-phase loads require the neutral line to function as intended. As these examples illustrated, any imbalance between L1 and L2 results in current traveling in the neutral line. Only in the very rare occasion with equal loads on the opposite phases does it result in no current traveling the neutral line. This is one of the compelling reasons circuit breakers make or break connection with the hot or high side of the distribution transformer rather than the neutral line. With this system in its present condition, with equal lighting loads on the two phases, a heater on L1, a motor on L2, and a clothes dryer L1 to L2. As one might expect, the single-phase loads experience exactly 120 volts, and the clothes dryer experiences 240 volts. Consider the worst-case scenario, in which all single-phase loads lose connection in the neutral terminal. No longer will voltage be equally apportioned between the single-phase loads. We might expect to observe some odd behavior. Allow me to demonstrate. Perhaps the only element in this system that doesn't change is the clothes dryer. The clothes dryer still experiences a 240 volt differential between L1 and L2 and will continue to draw 12 amps at an angle of negative 10 degrees. Everything changes for the single-phase loads. The loss of the neutral connection means these elements no longer experience a fixed 120 volt differential because they are no longer perfectly in parallel with a desired phase, but rather in series parallel with one another across the 240 volt differential between L1 and L2. A simplified diagram of the secondary minus the circuit breakers demonstrates the first lighting load and the heater are now in parallel with one another. Let's call this impedance Z single prime, which is a value of 17.1 ohms at an angle of 0 degrees. Similarly, the second lighting load and the motor are now in parallel with one another. Let's call this impedance Z double prime, which is a value of 15.5 ohms at an angle of 15 degrees. Z single prime and Z double prime are in series with one another across a 240 volt differential. An application of the AC voltage divider rule demonstrates that Z single prime, the parallel combination of the first lighting load and the heater, experiences a differential of 127 volts at an angle of negative 7.1 degrees. Similarly, another application of the AC voltage divider rule demonstrates that Z double prime, the parallel combination of the second lighting load and the motor, experiences 115.1 volts at an angle of 7.9 degrees. No longer is voltage equal between these single-phase loads. Understandably, current through and thus power dissipated by these elements lacking the neutral connection will also change. As if this wasn't odd enough, consider what happens when the motor turns off. The first lighting load and the heater remain in parallel with one another, presenting a parallel impedance Z single prime of 17.1 ohms at an angle of 0 degrees. Z single prime and the second lighting load are now in series with one another across a 240 volt differential. An application of the AC voltage divider rule demonstrates that Z single prime, the parallel combination of the first lighting load and the heater, experience 87.3 volts at an angle of 0 degrees. Similarly, another application of the AC voltage divider rule demonstrates the second lighting load experiences 152 volts at an angle of 0 degrees. The loss of the neutral connection has fundamentally changed the behavior and configuration of this system. It is for this reason one might observe odd behavior in a system lacking a neutral connection, such as unsteady lights flickering and dimming, or crazy motors surging and dying as loads are connected and disconnected. If you've ever had the misfortune of working on a house formerly owned by tweakers as I have, be aware that those fixtures that they haven't stripped and sold for scrap metal most likely don't function as intended because they're not connected as intended. Again, not only does the neutral line in a split-phase system carry imbalance current in the event of load imbalance between phases, it also serves to ensure single-phase loads have access to a fixed potential. Alright, that about wraps up this lecture. In conclusion, this lecture examines center tap transformers in split-phase or single-phase 3-wire systems. We examined split-phase systems in the balanced and unbalanced condition and discussed the role of the neutral wire. Remember to review these concepts as often as you need to really drive it home. Imagine how well a lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates. Get this picture for current through the dryer.